Alright, so today we're going to be learning about stars and we're going to be learning about the brightness of stars. Okay, so when we're talking about how bright a star is, the term is called luminosity. So this is what we're going to be talking about today. Before we get to that, we're going to do a brief recap on what we learned last week. So I'm going to give you a worksheet about the order of planets, since we're discussing like space and the solar system. So I just want you to fill out this chart, this worksheet, so I can see if you remember the planets in order. So here you go. Just take a minute or two to complete that. All right.
Finish.
Okay. Let me see. Okay, so you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. All right, good job.
Thank you.
Was that easy?
Really?
Okay. All right, so now we're gonna move on to the next part. Okay. So I'm gonna ask you a question, and once I ask the question, I want you to come up with a hypothesis. All right. So my question to you is, do stars that are closer to the Earth appear to be brighter than stars that are farther away from the Earth? So again, I'm going to give you a minute or two to come up with a hypothesis, and you're just going to write down what you think. But, you could agree with it or you could disagree. But make sure when you agree or disagree that you provide a reason why. So I need to know why you're agreeing or why you're disagreeing. So again, just take a minute or two to fill that out. Alright, so did you come up with your hypothesis?
Yes.
Okay, can you just read it out to me, please?
I think it's no for me.
Okay, why?
Because the bigger the star is, the brighter it was.
Okay, so you think size impacts brightness, right?
Yes.
Okay. Alright, so a lot of people think that, like, a lot of students, they usually think it's size. Like, size is what determines brightness. But in reality, is the distance. Yes, exactly. It's the distance that impacts luminosity, okay? So, for example, the reason why the sun is so bright is because it's a star that's very close to us. I have one more question for you, though.
Okay.
Do you think the sun is a big star, or do you think it's a small star?
It's the big star.
Okay, so the sun is actually a medium-sized star. There's a lot of different stars. There's billions of stars in space, and when we look at the size of the sun, it's actually a medium size. Again, it appears bigger and brighter because it's not very far from us. So I'm gonna put a video real quick, and in the video it's gonna describe luminosity, it's gonna describe distance, and it's going to describe a few new terms that will help you understand this concept, okay?
Okay.
And then after the video, we're going to move on to an experiment. So,
let's continue our chat from last time about stars that are not you. I mean, the stars in our universe. We've already talked about what a star is. A huge ball of hot gas that makes heat and light. Basically,
alright, so make sure you take that definition down.
Okay.
Last time about stars that are not you. I mean, the stars in our universe. We've already talked about what a star is. A huge ball of...
Alright, so you can write that definition down. Alright, so a star, again, is a bright object that gives off light by energy produced in its core. Alright, so the energy that a star produces in its core is what gives off the light. Alright?
Okay.
hot gas that makes heat and light. Basically, they glow. But how do they glow? And why do some stars seem to glow brighter than others? Let's tackle question numero uno first. How do they glow? All stars create energy in their core through a process called nuclear fusion. Sounds super cool, right? It is. Well, super hot actually, but you get the idea. It's neat. It's also way too complicated to explain in one video, so I'll just give you a really basic overview. The temperatures and pressures inside a star are so great that nuclear fusion, the same thing that powers hydrogen bombs, is almost constantly happening at the center of a star. Most stars are made up of mostly two kinds of gases, hydrogen and helium. During nuclear fusion,
Alright, so we just learned some good information right now. Okay, so basically it makes this energy because of nuclear fission, okay? Nuclear fusion, sorry. And another important piece of information that we learned in this video so far is that two elements that make up the sun is hydrogen and helium, alright? So make sure you take that in your notes. So again, the sun makes its energy through a process called nuclear fusion, and the sun is made up of two elements, hydrogen and helium.
Okay.
Alright, now we're going to continue the video, alright?
hydrogen molecules, really tiny units of hydrogen, smash into each other or fuse together to create helium. The enormous amount of energy that's created as a result of this fusion then travels out towards the surface of the star as heat and light and gives the star its glow. All stars go through this process to get their glow, but they don't all shine equally, leading us to our second question. Why do some stars glow brighter than others? Stars have different brightnesses.
Alright, so that question that she just asked, why do some stars glow brighter than others? Do you think you have an answer to that question?
No.
Okay. Alright, so just make sure you take notes as she goes over it.
Okay.
There are two major things that astronomers look at when determining how bright a star is. Its true brightness and its apparent brightness. Astronomers sometimes refer to a star's true brightness as its luminosity. Luminosity is a measure of how much energy or light a star shines from its surface.
Alright, so as the video just stated, there's two different brightness that astronomers look at, okay? So the first one is true brightness, and the second is apparent brightness, okay? So when astronomers look at true brightness, they're looking at the luminosity, okay? So I love that definition for you right here, so just make sure you take it down. So basically, luminosity is the measure of how much energy or light a star shines from its surface, okay? So again, when astronomers are looking at true brightness, this is what they're measuring. They're measuring how luminous a star is, alright?
Okay.
So just let me know when you're done writing.
I'm finished.
Alright.
Think of stars like light bulbs. Light bulbs with higher wattages or more power glow brighter, right? Same thing with stars. The more luminous or powerful a star is, the brighter it glows. When measuring luminosity, astronomers are considering how bright the star is as if they were in space, standing or I guess hovering right in front of it. That's why they call it true brightness. It's how bright the star really is, not just how bright it might look depending on where you are.
Alright, so another important piece of information. True brightness is basically how bright the star really is. Alright, just as the video said, it's as if we were standing in front of it and measuring exactly how bright it is. Okay?
Okay.
So, how does a star's size factor in? Some stars are really big, and some are really, well, not small, but smaller. So, if it's bigger, it must glow brighter, right? Not necessarily. Smaller stars sometimes have more power than bigger stars, just like smaller light bulbs can have more wattage than bigger light bulbs. Size also isn't necessarily important when measuring the second thing that astronomers look at when determining a star's brightness. It's apparent brightness. When we talk about apparent brightness, distance is a bigger factor than size. Since astronomers can't really go into space to see those stars up close because, they burn up and it would take too long to actually get to another star, they also measure how bright a star appears to us from a distance. This measure is called its apparent brightness.
Alright, so we just went over some good pieces of information, okay? So she basically answered your hypothesis from earlier when you said that the bigger the star is, the brighter it will be. Okay, so she just said when it comes to apparent brightness, size is not really a factor. The distance is what plays a factor in apparent brightness, alright? So the closer a star is, the more apparent brightness it's gonna have, the brighter it's gonna appear. The farther it is, it's gonna appear dimmer, even though it might have a true brightness that's more luminous. It's gonna appear dimmer because of the distance, alright?
Okay.
So let's continue the video.
Regardless of its size or its power, how near or far a star is to Earth plays a big part in how bright it appears to us. Not convinced? Let's take a look at two stars to see if the more luminous one also appears brighter to us Earthlings. First, meet Betelgeuse. Betelgeuse is a star, one of the brightest stars in the night sky, in fact. Betelgeuse shines with around 100,000 times more luminosity, or power, than the sun. So you need some serious shades to look at this guy up close. But how does that compare to the sun? The sun is a star we've all spotted from Earth way more times than we've seen Betelgeuse. Since we have no problem locating it, it must be bigger than Betelgeuse, right? Nope. I mean, don't get me wrong, the sun is huge. More than 1 million Earths could fit inside it. But it's not so big when you compare it to Betelgeuse. Because Betelgeuse is gigantic, about 400 times bigger than the sun. But because Betelgeuse is located much farther away from us than the sun is, it appears less bright to us. If the sun was located that far away, you'd need a telescope to see it at all, since it doesn't have as much power as Betelgeuse. So it's not the sun's size or power that makes it seem so big and bright to us on Earth. It's because it's so close to us, just 150 million kilometers away. So Betelgeuse is bigger and more luminous, or has a higher true brightness than the sun. And you'd be able to tell that if you could look at them side by side. But the sun has a higher apparent brightness to us on Earth because it's so much closer. So let's call this brightness.
Alright, so to sum up everything she just said, so let's break it down a little bit. So she just introduced us to another star, okay? So we have the sun and we have Betelgeuse. So Betelgeuse is about 400 times larger than the sun, and it shines about 1,000 times or more brighter than the sun. So it has size, it's bigger, and it's brighter than the sun. But because the distance of Betelgeuse is so far away, like very much farther than the sun, its apparent brightness is dimmer than the sun, alright? So even though Betelgeuse has a true brightness that's higher than the sun, because its distance is more than 1 trillion miles, like a quadrillion miles away from Earth, its apparent brightness is lower than the sun, alright?
Okay.
So that just shows you that the distance is what matters, alright, when we're talking about the brightness. The apparent brightness is distance, alright? So the sun appears brighter because it's at a shorter distance. Alright, so let's wrap this video up real quick.
Battle atop. To recap, stars glow as a result of the energy created in their core by nuclear fusion. That energy travels outward to the surface of the star, where it's seen and felt as light and heat. All stars glow because of nuclear fusion, but they don't glow equally. The amount of power a star has and its distance from us both influence its brightness. On that note, I think it's time for me to do some stargazing of my own. Astronomer Sabrina's out.
Alright, so at the beginning of the lesson, after your hypothesis, we talked about the size of the sun. And I told you that the sun is really like a medium-sized star. So now I'm going to give you a little chart right here that's just going to show you different stars, and it's going to show you how the sun looks, compared in size, how it looks compared to other stars. So right here.
Thank you.
Yeah, so right here, this is just the model that's basically showing you different stars, because as discussed earlier, I told you that the sun was really like a medium-sized star. So this is just showing you different stars that we have in space. So right here we see Betelgeuse that we just talked about, and this is Betelgeuse, and this is the sun right here, that small little dot. Alright, so this is the sun compared to Betelgeuse, Rigol, and other stars right here. Alright, so we're going to be moving on to the experiment part of the lesson. Alright, so our experiment is going to involve flashlights right here. So This blue flashlight is going to represent Betelgeuse, and this small red one is going to represent the sun. Alright?
Okay.
So, when I'm shining the flashlight right here, do we see how bright it is?
Mm-hmm.
So, that's the true brightness of the flashlight. Alright? These are the true brightness right here. So, we see how bright this is. So, in our experiment, we're going to put these two flashlights at different distances. Okay? So, the red one is going to be at a close distance. Okay, the smaller one is going to be at a close distance. And this one representing Betelgeuse is going to be far, like very much farther than this one. So, again, we're talking about distances. So, this one's going to be farther and this one's going to be closer. And we're going to basically model what the video was talking about. How distance plays a role in how bright a star looks. Okay? So, that's the experiment. So as we can see in the experiment right now, the flashlight that was representing the sun appears much brighter than the flashlight that was representing Betelgeuse. Now, as we discussed before, both flashlights are the same exact brightness. But because the one that represents the sun is closer, it appears much brighter, much more luminous than the one that's all the way back there. The one that's all the way back there just appears as a dim light, while this one that's really close appears to be bright and very luminous. So again, this just shows you that because the sun is a star that's so close to Earth, that's why it shines so bright. That's why it's so luminous. So this just shows you guys that distance is what determines the apparent brightness of a star rather than its size. Okay, so now that we finished our experiment, let's recap on the experiment. Okay, so the red light that was representing, well, the red flashlight that was representing the sun was much closer, so it appeared much brighter. The one that was representing Betelgeuse was much farther and it appeared dimmer. Okay, it was shining less bright. Both flashlights had the same brightness, the same exact brightness, but the distance made one look brighter than the other. Okay, just like the sun looks brighter than Betelgeuse and all other stars in the universe, simply because it's only 93 million miles away from us, which is a short distance in space. Okay, because distances go on for trillions and quadrillion miles. Okay.
Okay.
So now I'm gonna give you this worksheet. Okay. Basically, we're going off of the same question that we answered, that we went over at the beginning of the lesson. Okay. Do stars that are closer to the Earth appear brighter than stars that are farther away from the Earth? Okay.
Okay.
We already made a claim. Our claim is that stars that are closer to Earth are indeed brighter than stars that are farther from Earth. Okay, that's our claim.
Okay.
Now that we watched videos and we conducted an experiment, I want you to prove your claim. I want you to prove it and support your claim, okay?
Okay.
So you're going to prove it with evidence. Well, you're going to support your claim with evidence and reasoning. So using the video that we watched and using the experiment that we conducted, I want you to support this claim, okay? So here you go. Make sure you use the notes that you took. Think back on the experiment and think back on the video as well.
Okay.
Okay. All right. So, are you finished?
Almost. Okay.
Okay. Thank you.
You're welcome.
All right. So, okay, your evidence. Okay, for evidence, you mentioned the sun and Betelgeuse. All right. So that's some good evidence because that's, it's a reality. So yes. So because Betelgeuse is farther, it appears less bright. Because the sun is closer, it appears more bright. Okay. And your reasoning. Okay. So your reasoning again. You're mentioning that when a star is farther, even though it's brighter, is gonna appear dimmer because of the distance. Okay, so
Yes.
you're telling me that distance is the reason why a star appears brighter based on the apparent brightness,
Yes.
why it appears less bright. And you also mentioned the experiment with the flashlights. Okay, so even though both flashlights were the same brightness, the one that was closer was brighter, and the one that was farther was dimmer. Okay.
Okay.
Alright. So, we're gonna watch another video real quick. But before we watch the video, I just want to talk about Betelgeuse. So we mentioned that Betelgeuse is very far away, and we mentioned that Betelgeuse is huge and it's bright, like thousands of times brighter than the sun. So even though Betelgeuse is extremely far away from Earth, because it's so bright, we can still see it in the night sky. It doesn't appear as bright as the sun, but it still appears very bright to us. Okay, and we could see Betelgeuse when we're looking at constellations. Okay, if you're looking at Orion's belt, Betelgeuse is a star that makes up the constellation Orion's belt. All right, are you familiar with constellations?
Yes.
Okay. All right. So this video is going to teach you a little bit more about constellations. All right.
Okay.
We've spent the last few episodes talking about the effects of the atmosphere on the geosphere and the hydrosphere on the biosphere, as well as solving some pretty big engineering problems. So how about we take a break from Earth this time and talk about space? Now you might be thinking, but we've already learned about stars. Well, you're right, or at least you've been paying attention. But we learned about individual stars, basically how they do what they do as solo acts out there in the universe. But what happens when a bunch of stars band together?
All right. So do you see this this group of stars right here?
Yes.
This is exactly what I was talking about. This is Orion's belt, and this star is Betelgeuse right here. Okay. So do you see how groups of stars can create like an image?
Mm-hmm.
All right. So I'm gonna let you watch the rest now.
Okay.
Form a supergroup, sort of like the Avengers of the night sky. Well, then they're called a constellation. Today we'll talk about these groups of stars and why they're so important to astronomers, besides being just plain cool. Or hot. You know what I mean. So, what exactly is a constellation? A constellation is a cluster of stars in the sky that have been grouped together in a pattern or shape in a...
All right. So make sure you read the definition for constellation.
Mm-hmm.
Okay. So it's basically a group of stars it's a group of stars in the sky that are grouped together in a particular pattern. All right.
Okay.
So a group of stars that are grouped together in a particular pattern or shape and have been given a name. Okay?
Okay.
Alright. Let me know when you're ready.
I'm ready.
Alright.
been given a name. But before we take a closer look at constellations, let's review what a star is. Remember, a star is a bright object in space that gives off light through energy that it makes in its core. The sun is the most famous star to us Earthlings. We've already talked about a few other well-known stars, though, like bright Betelgeuse. Astronomers use bright stars like Betelgeuse as markers in the sky to help find other, less bright objects in space. For example, if you were looking for a dim star like Sirius B, you might have to look for a long time to spot it among the many other stars in the sky. But if you're able to spot a much brighter star like Sirius A, and you know that Sirius B is located to the lower left of Sirius A, then it'll be much easier to find Sirius B. Like I said, there are so many stars in the sky that trying to spot just one can be tough, especially if it's not near a bright one like Betelgeuse or Sirius A. That's where constellations come in. Astronomers use constellations to help them better map the night sky. Think of stars like cities on a map and constellations like countries. Finding a large shape in the sky made of many stars is a lot easier to spot than trying to find one single speck. Plus, there are only 88 named constellations, which is a much more reasonable number to deal with than a billion. And most of the 88 recognized constellations came from the ancient Greeks. The stars in a constellation aren't related in any particular way. They just form a shape that the Greeks used to tell stories about their gods, goddesses, and mythical creatures like flying horses and giant scorpions. Now that we know what a constellation is, why don't we get to know some of of the more famous ones.
Alright, so I just want you to pay attention, take some notes as well. Like, she's gonna name some famous constellations, alright?
Okay.
Harry Potter fans will recognize the name of our first constellation. Its name means dragon in Latin. It also happens to be the name of Harry's biggest nemesis. Well, second biggest after he who must not be named, of course. Yep, it's Draco. According to legend, Draco was a dragon killed by the goddess Minerva and was tossed into the sky. Draco is one of 48 constellations described way back in the 2nd century by Egyptian astronomer Ptolemy. People have been seeing this dragon-like shape in the night sky for a long time. Constellations aren't just named after creatures, though. Some are named after mythical people, particularly gods and goddesses. One of the more well-known Greek gods has his own constellation, and a Disney movie. I'll give you a hint. He'll go the distance. It's Hercules. The stars in the Hercules constellation take the shape of the mighty hero as if he's holding a bow after just releasing an arrow. You go, Hercules. The name of our next notable constellation also makes an appearance in the Hercules movie as a super cute winged horse. Say hello to Pegasus. According to Greek mythology, Hercules never actually rode Pegasus like in the movie, but the flying horse did spend some time with Zeus, king of the gods. Zeus liked Pegasus so much he transformed him into a constellation and placed him in the night sky for everyone to see. Now, you're familiar with at least 3 of the 88 constellations in our sky, only 85 more to go. As the Earth rotates, you'll see Draco, Hercules, and Pegasus, plus all the other constellations over the course of a year. But more on when and where you can see the constellations in the next episode. So now you know what a star is, and that a cluster of stars in the sky that are grouped together in a particular pattern is called a constellation. Besides having really cool shapes and stories behind their names, constellations help astronomers and us map the night sky. Since space is so huge and massive and ginormous, our map is far from complete. So anything that helps us navigate that vast, well, space of space is okay by me. Thanks for the help, constellations.
Alright, so now that we learned about constellations, I have one more activity for you that's gonna be based on constellations, alright? Alright, so your next worksheet, you're gonna find the constellation, alright? So, here you go. Just make sure you follow the dots, alright? So you see the dots go from 1, 2, 3. So just make sure you follow them as you connect the dots, okay? And then once you connect the dots, tell me what constellation you see based off the ones that we just watched in the video. It might be Hercules, Orion's Belt, Draco. So you just make sure you tell me which one you see. Alright, how's that worksheet coming along?
Good.
Are you almost done?
Yes, I'm finished.
Okay. Alright, so it looks like you're done. Can you tell me what constellation that is?
It's Orion's Belt.
Alright, let me see. Yeah, good job. You're right.
Thank you.
So yeah, this is the constellation. This is Orion's Belt. Okay. So good job. Here you go. All right. So class is almost over. We have a couple minutes left, so we're gonna do this last activity. Okay. We're gonna do a scientific math problem. All right. So our problem, we're gonna try to figure out how long it takes sunlight to reach the Earth. All right. So I'm gonna give you guys some new information. So make sure you guys get your notes ready. Okay. So the first piece of information I'm going to give you guys is something that we already know because we discussed it many times. So the sun is 93 million miles away from the Earth. All right, you guys already have that. Now this new piece of information, make sure you guys take this down. So light travels 186,000 miles per second. Okay? Light travels 186,000 miles per second. So knowing the distance of the sun from Earth and knowing that light travels 186,000 miles per second, I want you guys to figure out in minutes how long it takes sunlight to reach the Earth. All right, so take your time, think about it. Are you having trouble?
Yes.
Okay, so let's do this real quick. Come here. All right, so I asked how long does it take sunlight to reach the Earth. So we're gonna start with the distance of the sun from the Earth, which is 93 million miles away. So we're just gonna put that in our calculator. So right here we have the distance of the sun from Earth. So now we're gonna take the speed of light. So light travels at 186,000 miles per second. So what operation do you think we're gonna use with these two numbers, 93 million and 186,000? What operation do you think we're gonna use?
Divide.
Yeah, you're right. So we're gonna divide that. Okay, so we're gonna divide 93 million by 186,000. So when we divide these two numbers, we get 500, okay? So we get 500 seconds. Now, if we're talking about minutes, okay, 1 minute is 60 seconds. So we're gonna have to divide 500 by 60. And when we do that, we get 8.3, which in minutes equals 8 minutes and 26 seconds. So sunlight takes about 8 minutes and 20 seconds to reach the Earth. All right. So that's how you solve that. That's how you get that. All right. So we're gonna take a quick virtual tour around some stars using the app Celestia. So as you can see right here, this is Earth. All right. So let's take a quick look at the sun real quick. All right, so this is the sun right here. All right, now let's look at Rigel. So Rigel is a star in Orion's belt. So since it's in Orion's belt, it's visible. You know, you can see it in the night sky with the naked eye. All right. So right here is Rigel. As you can see right here in the description, its luminosity is 52,200 times more luminous than the sun. All right. This star is also very far away, but because it's so bright and luminous, like we could see it with the naked eye. All right. So next one we're gonna look at, we're gonna take a look at Betelgeuse since we talked about it so much. All right. So as discussed, Betelgeuse is a star in Orion's belt. And again, we can look at this description right here, and we can look at the luminosity. It's about 14,000 times more luminous than the sun. Again, so Betelgeuse is about 642 light years away, and a light year is about 6 trillion miles away. So Betelgeuse is like quadrillions of miles away. That's how big the number is. I know this number is too much to fathom for a lot of you guys because you guys are just in 5th grade, but I'm just giving you like an idea of how far it is. So despite being quadrillions of miles away from the Earth, it's still visible. So that's just a testament to how luminous the star is. All right, so that's it with our virtual tour.